Assalamu alaikum, sir. This is the project demonstration of the group Minimints. The logic and memory modules will be discussed by Ashriya Farhin. The board and winning modules will be presented by Mumtaza Mubashira. Sadia Tabassum will explain the player selector module. And I am Tahia Hussain, and I will begin by describing the dice module. So this is the dice module. The clock pulse for the dice module is generated by a 555 timer IC, which is manually triggered using the dice button. When the button is pressed, the clock pulse activates the JK flip-flops, providing a 2-bit binary inputs. These inputs are then displayed on the 7-segment display. To prevent the dice from showing a 0, we use a NOR gate and a XOR gate to eliminate the 0 output. This ensures that when the clock pulse triggers the dice, the values cycle through 1, 2, 3, and then back to 1, never displaying a 0. Once the dice button is released, the dice pauses and displays the current value. The speed of the dice is controlled by adjusting the frequency of the clock pulse generated by the 555 timer. Increasing the values of the resistor and capacitor decreases the frequency, eventually slowing the dice down. Conversely, decreasing the capacitor value increases the speed. So now I will demonstrate how the speed of the dice can be adjusted. So now I will run the simulation. Mm, Once the simulation is running, pressing the dice button triggers the clock pulse, and we can see here we can see that the dice is generating random values between 1 and 3, and right now the speed is quite fast. Once the dice button is released here, um, the dice will stop and hold at a random value, displaying whichever number was shown at the time the button was released, and then it again starts oscillating. So if we want to slow the speed down, what we can do is increase the capacitor value. So now after pressing the dice button, we can observe that the frequency has decreased and the time period has increased, effectively slowing down the dice. So in this way, we can control and adjust the speed of the dice in our circuit and stop it at a random value. Now showing the board module, it is 4 by 4 grid. Here 4, here 4. Row wise, column wise 4 by 4. Now it has, one grid has 16 LEDs. In one row, there is four blocks. One block contains four LEDs. That mm, that contains the player 1, player 2, snake and ladder. This board module is from 0 to 15. It has been numbered. So here the LEDs are connected through powers to power up the LED, and here the position has been the position indicated by player position decoder and snake and ladder position decoder. Here if I go to child sheet, to show the snake position and ladder position, snake start and snake end, snake start and snake end, here two decoders are used, and for same as ladder. In this way, this ladder and snake is connected in the board, and now showing the four components here. Here, this red LED is the player 1, blue LED is the player 2, and this green LED is the ladder, and yellow LED is the snake. For testing the board module, if it works as it should, we have to run this. Here, the player position is at 0 position. Now, if I want to
if I want to if I want this to go to position 7, we have to change the input here. The LED went to 7, position 7. The same for blue LED. If I want this to go to position 12, then we have to change the input here, here. The LED came here again. For snake, here the start is at 11. Now if I want this to come to 11 to 3, then 11 to 3, then I have to change it. So the snake is from 11 to 3. Now the ladder is at 0 position, ladder start, and ladder ends at 6. Now if I want it to be from 5 to 12, I have to change it. For 5 to 12, here 5 to 5 to 12, this. Now the ladder is from 5 to 12. So we have to change the inputs to change the positions of every LED.
So this is our snake ladder's total module. So this represents the player's position here, and this represents the dice values here. And now this should be added. So we have used a 4-bit binary adder here to add this. Now we have to check the sum for two cases. The first is, if the first case is for the ladder case and the second is for the snake case. We have maintained a sequence here. We have maintained a sequence here in such a way that this part, totally this part here, works for ladder checking procedure, and from the output of the ladder checking procedure it goes to the rest of the part, which is our snake checking procedure. So it maintains a sequence here. It will first check the ladder thing and then it will check the snake part. No and we've created the both things in a similar way. So first it goes, the sums are going to the input as input of a comparator, and the ladder start is going to the other input. So if a is equal to b, it will give us one value, which are ended here again with the sum values, so that if it is 1, it will give me some values here. If it is 0, it will give me 0 values here. Now it is actually taken as another input of a 4-bit binary adder, which adds the adder length here. So now it will give me another sum values. These sum values are again ended with the a is equal to b position here. So that with the a is equal to b position here, again ended with the a is equal to b position here, so that we get either 0 values here or the sum values here. So now this is the a is equal to b part for this for the ladder here. Now for what happens if a is less than b, a is greater than b. We have used the similar procedure. We have actually ended them again individually with the sum values coming from here. And these four are for a is greater than b. We have again ended them individually with the sum values here. And now either it will give me 0 values or 1 values or the sum values. So these are again individually. The sum one from a is less than b, the sum one from a is greater than b is actually added individually with the OR gates here, so that we get a total output for these two cases, a is less than b and a is greater than b. So this and this are the two outputs of the snake. Whether this will give me values or 0, this will give me values or 0. So now these are added with OR gates, so that we can get a total output of a ladder case. So now the ladder case is going to be our new input for the snake checking part. So these are our new sum. This is taken as the input of a comparator for the snake checking part, and this is the snake start. Similarly, we have designed. So if a is equal to b, then we have used AND gates and ANDed them individually with the sum coming from here. And this is again taken as input of a 4-bit binary subtractor, and the other inputs are coming from snake length here, so that it can subtract. And then again these are ANDed with the a is equal to b coming from here, so that we can either get 0 values here or some values here, depending on the a is equal to b value here for the snake part. Now this is one output of our snake part, and now for a is greater than b and a is less than b, we have used a similar procedure here, added them individually with this sum, added them individually with this sum, then added them with OR gates. Now this is our output for the other two cases, and this is our output for a is equal to b case for the snake. And now we have added them with now we have added them with our OR gate, so that we can get a final output here. So if we run the simulation, this is 0 0 1, this is 1 0 0. For suppose this is so this is our testing part for snake ladder module. This represents the player's previous position. This is dice value. This is our ladder start. This is our ladder length. This is our snake start, and this is our snake length, and this is our output. So if we run the simulation, then we are getting 0 0 1 for previous position, and this is the dice value is 1. So the 1 and 1, it should give us the output of 2, as it doesn't match with anything else. So if it matches with the ladder start here, which is set as 3, then it should add the 3 with 1 and give us output of 4. So this is 0 1 0 0 4. So if it matches with the snake start here, which is 5 0, there is actually 1 and 3. Now if we add 4 here, it should match with the snake start. So snake start is 5 here, so the 1 should be subtracted from 5, so it should give us output of 4, which is 0 1 0 0. So this is our memory module. These are multiplexers, 4-bit multiplexers, and these 4 are D flip-flops for player 1 position, and these 4 are D flip-flops for player 2 position, and this represents our snake ladder output, and this represents the output coming from player 1's LED, and this represents the output coming from player 2's LED, and this represents the dice signal, and this is player 1's position, and this is player 2's position. So so if we have designed the whole process in a way that if we get 1 value here, it will update player 2's position. If we get a 0 value here, it will update player 1's position. So if we run the simulation, the dice value is 1, and we are not getting any signal from the player 1, we are getting signal from player 2, so it should update the player 2's position, which is 1 0 1 0. So here the player 1 is not updated, the player 2 position is 1 0 1 0. Now if we change the signals here, player 1 is 1 here and player 2 is 0 here, so it should update the player 1's position. If the snake ladder value is something like 1 1 0, then it will update the player 1's position here. So this is how the whole thing works. And now coming to the reset part here, we have actually used this very simple procedure for reset part. If we design the hardware case here, we will add some power here with a LED light at the hardware part, so that when the LED is switched on, it will give me 1, so that it will give me values here. When the power is gone in our hardware, it will give us 0, so it is restarted here. So this is our total restart procedure.
Player selector module. The player selector module is designed by using a D flip-flop to toggle between two players. We use a 555 timer for generating a clock pulse in the D flip-flop. We use some capacitors and resistors to improve and smooth the circuit. In the 555 timer, ground and VCC connections are for the stability of the circuit. In the D flip-flop, Q output represent player 1 and the Q bar output represent player 2. The D input is connected to the Q bar output through a 10 kilo ohm resistors, which ensures the flip-flop toggle states on each clock pulse. The Q and the Q bar output controls two LEDs. One is blue and one is red. The blue one is for player 1 and the red one is for player 2. And there is a 330 ohm resistors which limits the current for both blue and red LED. In the D flip-flop, a switch button is connected to the reset pin and it toggles between two players, and the set pin is connected by 5 volt. When the switch is on, and Q is equal to 1, that means the blue LED turns on and the red LED turns off. But when the switch is off and Q is equal to 0, that means the red LED turns on and the blue LED turns off. The toggling action helps in randomly selecting which player will start the game. For testing the player selector module, when the switch is on and Q is equal to 1, then we can say that the blue LED is on and the red LED turns off. But when the switch is off and Q is equal to 0, then we can say that the red LED turns on and the blue LED turns off.
Here showing the winning module. For winning module, there are two comparators used for player 1 and player 2. Here, this is the signal that comes from the memory output. The current player position, and here is the condition that this position should be 15. So, and here if the condition is A equals to B, then the player will win the module. Then the player 1 will win, and this LED will light up. And for this player 2, the condition is same. So here showing here position 1 for player 1, the condition fulfills, so the LED lights up.
So this is the dice module. When the clock pulse is triggered using the manual switch, it sends an input to the JK flip-flops, which then generate a binary output. This output is connected to the snake and ladder logic module, continuously updating the dice value based on the number that is displayed on the 7-segment display. This portion is intentionally grounded to ensure the formation of a 2-bit output. Additionally, the dice button is connected to the game memory, allowing the dice values to be automatically updated in the memory in this position.
This is our snake ladder logic module, responsible for processing the game logic. The inputs are here: player position, snake start and snake length, ladder start and ladder length. These inputs are connected to a decoder which processes them and passes the data to the module. The module calculates the player's updated position based on snakes and ladders. The computed player position is then sent to the memory module for storage. The input to the memory module comes from player 1's LED and player 2's LED. We use a manual button to trigger the LED for a player. When any player's LED lights up, it sends a signal to the memory module. The memory module updates either player 1's position or player 2's position based on the input received. The updated player positions are then sent to player 1 and player 2 decoders, which display the final position for each player.
Here for the integration part of the board module, it is board module is actually connected to the decoders, position decoders, player position decoder, ladder and snake position decoder. All this player position decoder is connected to the memory module output. Memory module output here, it memory module gives output to the player position decoder input, and then this decoder finds the position, and those positions LED lights up. And this ladder position and snake position, these two decoders are connected to the snake ladder module, snake ladder logic module. Here snake ladder logic module uh, uh, gives output to the sorry, here this gives output input to the ladder position decoder and snake position decoder. And from this here snake and ladder position is indicated. In case of winning module integration, here winning module is connected to memory module. Here memory module's output is also connected to the two comparators input. These comparators input, and uh, how we will know which player will win. For this, the selected LED. If LED red LED is selected, then red LED is selected, and if it goes to position 15, then it will show that it will light up the red LED. Here, that's why player selector module and the winning module is connected through an AND gate. And the memory output gives the current player position to know if it fulfills the condition.
Now I will explain the game demonstration. Player 1 is activated. If the dice value is 1, then the game will start, and otherwise not. Here the dice value is 1, that means the portion will upgrade from 0 to 1. Again, when the dice value is 1, that means it will go to portion 2. Now the dice value is 3, that means the new portion is 5. Again, the dice value is 2, that means the new portion will be 7. After rolling the dice value, now dice value is 3, that means it will upgrade to 7 to 10. Again, when we roll the dice, it will upgrade from 10 to 13. And again, when we roll the dice, the dice value is 2, and the new portion is 15. That means the last portion and winning portion, that means the player 1 is win the game, and the winning module is, and the red one is the red LED is turned on. Similarly for the second player, that means the blue one, it will upgrade from 0 to 3. Again, when we roll the dice, then it will change the position. Now the dice value is 3, that means it will upgrade from 0 to 3, and again the dice value is 3, that means it will go to 3 to 6. This is the game demonstration of our project. Thank you for watching our project.